Hello and welcome again to my Physics Online video lecture series. In today's video, we're going to be continuing our discussion of RLC circuits and AC signals applied to RLC circuits. And we're going to do that today by way of discussing impedance. Now, there's a few things that we need to sort of keep in mind in the background of this video. So we should recall a few things. One of them is that the reactance of a circuit, of a device, tells us the ratio of peak voltage to peak current for a circuit element or for the device in question. Thus, our reactance as a general rule is defined as V naught over I naught. And this was given for different elements within the circuit as either omega times L, or for a capacitor 1 over omega times C, or for a resistor, we don't usually refer to this as reactance, it's just simply the resistance. Second thing to recall is that AC signals tend to end up having phase shifts for different elements between the voltage and the current. That is, we expect for voltage to lead current within an inductor, we expect current to lead voltage within a capacitor, and we expect the two to be synchronized within a resistor. Finally, these phase shifts can be represented by phasor diagrams. Last but not least, we might add in exactly what it is that the Kirchhoff voltage law, the loop rule, is telling us in these cases in the context of a phase diagram. Something like the total voltage, or the voltage of the power supply, if you will, must be equal to, albeit maybe in opposite polarity from, the voltage drop across the inductor minus the voltage drop across the capacitor quantity squared, plus the voltage drop across the resistor squared. And that actually is just kind of a application of the logic of the phasor diagrams. Technically, these are peak voltages for what it's worth that we'd want to use in this particular equation. And this one right here comes from the phasor diagrams, comes from the logic behind the phasor diagrams, and it's sort of our main jumping point for today video, because what we want to do today is in some sense determine the value for our let's say voltage from our power supply given a series of elements, an RLC circuit that it's going to be applied to. And by the way, this works for an RC circuit, it works for an LC circuit, it works for an RL circuit. So one of the elements could be missing. In fact, two of the elements could be missing, and this will still work. We just have to sort of strategically put some zeros in. So the peak voltage equation, given this, and given this line at the top, we can sort of rewrite the voltage for the power supply. And what we end up getting is that the sort of voltage for the source, the peak voltage for the source, must be the square root of, and really what we want to do is just kind of convert all these things into currents where possible. So this ends up being essentially the peak current times, or the peak current squared, if you will, times the reactance, omega L, for the inductor, minus the reactance, 1 over omega C, for the capacitor, again, plus that peak current times the resistance squared. And so I can easily pull the peak current out. And so my sort of source voltage is now equal to I naught times the square root of omega L minus 1 over omega C quantity squared plus R squared. So I've pulled out an I naught squared from everything, and since it's square rooted, it's like pulling out an I naught. Now this current, this is the current for this system as a whole. It's also therefore the current that the source has to be putting out. So you could call it the source current if you'd like. We define here a new or semi-new term called impedance. And I've already kind of mentioned impedance in my previous videos a few times. Impedance is to the circuit as a whole, or for that matter to the source, what reactance was to each individual element. Now it should be evident from this sort of definition for impedance that the impedance is going to be given by basically this equation here that I've sort of highlighted, divided on both sides by the peak current I naught. So basically what that's letting us do is define the impedance for the circuit as a whole, Z, and it's given by the square root of omega L minus 1 over omega C quantity squared plus the resistance squared. So notice that this impedance, this is actually a sum of squares, so both this quantity as a whole is positive and this quantity is positive. So the impedance is real. It's going to give you that ratio of V naught source over I naught. So in some sense, we could say down here that Z is defined as V source 0 over I 0. But this right here is the actual equation for determining the impedance for our system. Let's look at a quick example of impedance before continuing on with our lecture here. We want to know what the impedance is going to be for an RLC circuit given a resistance R of 10 ohms, an inductance L of 5 millihenries, or 5 times 10 to the minus 3 henries, a frequency of 120 hertz. That means that the angular frequency is 120 times 2 pi radians, and a capacitance of 20 microfarads, that is 2.0 times 10 to the minus 5 farads. So the impedance, again, is given by the square root of the basically the reactances of the inductance, the inductive reactance, and the capacitive reactance subtracted from each other and then squared, plus the resistance squared, or using the formula obtained at the end of the last slide, we're looking at omega L minus 1 over omega C quantity squared minus or plus, R squared. So Z, the impedance, should look like the square root of, and our first term is basically omega times L. So we're looking at basically 240 pi times 0.005 Henry minus the capacitive reactance. So that's basically a 1 over 240 pi times 2.0 times 10 to the minus 5 farads. So that is 0.00020 farads. quantity squared plus 10 ohms squared. That latter part maybe is the easy part. So that's basically stuff that we'd put into our calculator. And so what we end up getting for our total impedance of this circuit is square root of 4011.8. And so what that comes to is about 63.3 ohms. Maybe keep two significant figures. So we're looking at about 63 ohms. And that is your total impedance for this entire circuit. A good follow-up question to this one might be, what if we had a capacitor whose capacitance was 5 times larger? In other words, what if instead of 20 microfarads we had 200 microfarads? Well, if that were the case, then this number changes from 66.3 ohms to about 6.63 ohms. And so instead of 3.77 minus 66.3, you now have something like 3.77 minus 6.63. And that gives you negative 2.86. Square that, you get 8.17. And that's pretty comparable to this 10 ohms resistance that you have. So, add your 100 ohms of R squared value and take the square root, and you end up with a value of Z is about 10.4 specifically. So 10.4 ohms becomes your new value. Much lower, in fact, comparable to just the value of R, the resistance. Now there's a second thing that we can define, and it's maybe worth redrawing our phasor diagram for an RLC circuit generically. And that second thing that we can define is what's called the phase angle for the circuit. And so, let's say that our circuit is such that this right here, this first arrow could represent our current at a given time. So this is I naught. That means that at that same time, the voltage drop across the resistor, VR, would be represented by this second arrow here. And it means that our voltage drop for the inductor and for the capacitor are going to be represented by this pair of arrows that I'm going to draw here, VL naught, and then for the capacitor, maybe VC naught. So VC naught. Note that VC naught plus VL naught would be maybe this arrow right here. So let's draw an arrow. I'm just offsetting it a little bit for visibility purposes. So this is VL minus VC. All right, that means that our overall for the circuit sort of voltage, our power supply voltage, if you will, is this vector right here, or this phasor right here. So this would be V, variously called V naught or VS naught. Okay. Now, there is going to be some angle phi between the voltage across the resistor and the voltage across the source, assuming, of course, that we have a capacitor and an inductor and that our omega is non-resonant. When it's resonant, then VL naught and VC naught actually will add to 0, as it turns out. So you can figure out what's the resonant condition just from that. Basically, if the voltage across the inductor and capacitor are both equal in peak, then the output voltage from the source just matches the voltage across the resistor. That's sort of the consequence of this, because the other two will have canceled out, or this little VL0 minus VC0 arrow has a height of 0, in other words. Using a little bit of geometry here, so you could even call it like right triangle geometry. It should be obvious that the tangent of the angle, of the phase angle phi naught, should be the opposite, which again is V L naught minus V C naught, divided by the adjacent, which is V R naught. Now, in terms of the current and of the reactances, this ends up being the reactance of the inductor minus the reactance of the capacitor divided by the resistance. There's a I naught term on both top and bottom that cancel. Also, perhaps useful would be the cosine of this phase angle. The sine of the phase angle could also be used, but very often it's the cosine that's given. The cosine should be the adjacent divided by the hypotenuse, and this hypotenuse, VSO, is the I naught times the impedance Z. So what we'd be looking at for this cosine of the phase angle is the voltage across the resistor divided by the output voltage, which in turn is just the resistance divided by the total impedance of our system. This leads me to kind of the final concept in today's video, which is what's called the power factor of the circuit. The power factor is just telling us how much power is being dissipated by the circuit, or in other words, how much energy is being lost per unit time within the circuit. To consider power factor, we need to recall a couple of little things. The first is that inductors and capacitors don't dissipate power, only resistors. The second thing to recall, or if you count this as two things, I guess the third thing or the second part of the first thing to recall, however you want to slice it, is that power dissipated by a resistor, generally speaking, is I times V, but we usually switch that over to I squared times R. So in the case of an RLC circuit, the power dissipated, we might look at average power since we're looking at an AC signal. Thus, we're looking at, for current, the RMS current. And so in some sense, we would say something like P average is IRMS squared times R. But we want to do this in terms of the impedance of our circuit and of this sort of phase angle. And so in terms of those things, the average power being dissipated, again, you can use IRMS squared. That should actually be 1/2 I naught squared for what that's worth. Looking at this phase angle, if I want to get R isolated from Z, R is Z times cosine phi. So this ends up looking like IRMS squared times Z times cosine phi. And that duplicates for me the other equation that I had before with DC power and an ohmic resistor only. All right, so last little point before we move on to our example. I started this by saying we're talking about power factor. I ended this slide so far by talking about average power dissipated. So where's the power factor actually come into play in all this? Why am I not just talking about power? This cosine phi term is what's sometimes called the power factor for the circuit. And so that's also why on this previous slide I defined a tangent of phi and I defined a cosine of phi, and I mentioned you could also do the sine of phi, but I didn't really work out the sine of phi. It's just not as interesting as the tangent and as the cosine in this phase diagram. So let's go ahead and work an example or two, maybe a quick example of two parts. So given the previous RLC circuit, that is the circuit that I worked this example for before, what is the power factor and what is the resonance frequency for this circuit? Okay, so note that what I had previously found for this circuit was that the impedance Z was 63 roughly ohms. So I can actually write out more digits. It's not just 63 ohms. The calculation came out to 63.339032222 ohms for what it's worth, and we just retained 2 digits of precision. And then we have this frequency 120 hertz for which this was the impedance. So the power factor that we're looking for here would be cosine phi. And cosine phi, again, is given by R divided by Z. So that's 10 ohms, because R was 10 ohms before, divided by 63 point, let's say 3, etc. ohms. If I plug that into my calculator, I end up getting a power factor of about 0.15788. So let's call this a power factor of 0.16. Now note that a power factor of 1 essentially means that the impedance and the resistance are equal, and so we're dissipating a lot of power. And at the other extreme, if I have a power factor of 0, that essentially implies a very, very large impedance, or in other words, just 0 resistance. So I either have a lot of a large capacitive reactance or a large inductive reactance, or both, compared to the resistor, and so very little power would be dissipated. So this power factor is basically telling us what fraction of the possible power that could be dissipated is actually being dissipated. The other part of this question was to determine the resonance frequency. So remember our little aside here that resonance occurs when this angle basically is 0, when this voltage drop is from the supply is equal to the voltage drop across the resistor, which is the condition that omega L equals 1 over omega C. Now we've got an L and a C value kind of fixed. I'm looking at omega L is equal to 1 over omega C. That's the same thing as basically saying that omega squared is 1 over L times C. So that is 1 over 5.0 millihenry, so 5.0 times 10 to the minus 3 times 20 microfarad, so 2.0 times 10 to the minus 5 farad. And so that gives me omega squared is 1 over 1.0 times 10 to the minus 7 seconds squared. And so that basically means that omega is 1 over the square root of 10 times 10 to the 4 inverse seconds. If I want the frequency to be frequency f, then I got to divide that further by 2 pi. What I end up getting when I do that is about 5.0 times, or 5.032 times 10 to the negative 6 hertz. So that is the resonance frequency for my circuit. Alright, well that is all for today's video. You have hopefully learned something from watching it, and as always, Thanks for watching.